What I want to do today is talk to you some about a new model I've been working on, a new approach for estimating selection on polygenic traits when it varies in space and time because of fluctuations in the environment. And we know that the relationship between phenotype and fitness can vary over both space and time, and this consequently, the direction and magnitude of natural selection can vary over space and time. Now this can occur because of shifts in the abiotic environment, such as when extreme precipitation events across time drive selection for larger or smaller, weaker body size in Darwin's finches. It can also involve things like antagonistic coevolution or cases of negative frequency-dependent selection, as we see in Tamima Christina's insects, where even though one morph is generally more cryptic on one of two different host plants, they become really common to get selective and you get fluctuations like you see here. Now, I'm interested in fluctuating selection in part because I think it has important ecological and genomic consequences. Strong but fluctuating selection has the potential to cause rapid shifts in ecological or ecoevolutionary dynamics. It can have both promote stability and persistence, and it can have effects on things at the community or ecosystem level. For example, that same strike phenotype in Tamima Christina's stick insects that experiences fluctuating selection can affect arthropod abundance, arthropod richness, and have important ecological consequences. I also think it's interesting because one of the key expectations for climate change is an increase in variance of environments, not just means. So we expect maybe more fluctuating selection over time. There are also potential genomic consequences. Fluctuating selection has the potential to maintain functional genomic variation, and it may be important for affecting diversity levels overall, or perhaps not. So with that in mind, what I want to think about today is, can we use population genomic time series data to detect fluctuating selection when we're thinking about a polygenic trait? So what I'm thinking about is, can we use changes in allele frequencies across multiple populations over time to think about fluctuating selection? Now, I've done this some already thinking about individual loci, and the key trouble there is that if you are looking at fluctuating selection where you might have strong selection in individual generations, but not consistent over time, the patterns for selection and drift are pretty similar. So your quantile plots looking across simulations that mean change from drift and selection, and standard deviation and change in different selection distributions are largely similar. Where you have more power is when you can tie changes to individual environmental factors or covariates. So look at the covariation between the environmental state and change. You get a much striking difference between what drift does and what selection does, different distributions of change. This works fairly well when you have strong selection on individual loci, not as well when you're thinking about a polygenic quantitative trait, because even with strong selection on the trait, you can have weak selection on individual genetic variants. So the way I think we can fix that is by tying the trait variation of the trait that's under selection to the effects of individual alleles on that trait, so we can sort of suck them up together and not have to look at what individual loci do. So what I want to think about is a model that connects trait variation and genetic variation. Now, you could ask at that point, well, why not just study the trait? You could just measure selection of the trait directly. That's a fine thing to do. There's a couple of benefits of thinking about things this way, though. One is that we can better isolate the component of change in a trait that's due to evolution or genetic change versus just plasticity. It also means we can think about measuring and analyzing the trait under controlled conditions and not having to phenotype every single population over time. And lastly, even though we're not directly focusing on the individual loci in terms of selection, we can have derived parameters in our model to capture the selection on those individual loci. So to think about this, we need a population genomic time series, a model for how genotype relates to phenotype, so results from genome-wide association mapping or genomic prediction, and an understanding of the relevant environmental variables. So really, I got to know what's going on in the system. So I'm going to talk to the model, and then I'll present some results showing you where it works and where it fails. So the basic idea is we're going to start by thinking about a selection differential. It varies as a function of the environment. You can have that selection differential vary linearly with the environment. The step function, sigmoidal, other things are possible. These are the three I've done so far. And in the simplest case, linear, you just have some average selection coefficient, selection differential, A, and then some effect B of the environment. The other ones are a tad bit more complicated. I'll focus mostly on the linear one. Make some other comparisons. Now, we have a selection differential varies with the environment. We want to now be able to connect that selection differential to change individual loci and selection on individual loci. We can do that by thinking about the marginal fitness of an individual with some allele that affects the trait, which is simply a function of the distribution of trait values given having that allele, and their fitness is denoted WI. That's very much tied to this thing, SI, the selection coefficient for that individual allele, which can be approximated if you assume linkage equilibrium and assume that you have weak selection of individual loci by the effect of that allele BI on the trait times the selection differential over the phenotypic variance. So there's our selection differential coming in, the key thing in our model, and our estimate of how we relate trait to gene. From that, we can get the expected allele frequency change due to just selection at that locus, and we can put that in the context of our Fisher model to add in genetic drift. I can do all this in the context of approximate Bayesian computation because it makes things really flexible. In that context, we first have to sample values for A and B, the things that give you the mean and the effect of the environment on selection. I'm using these spike and slab priors for that. The reason for this is that it lets us have zeros, so no selection is a real possibility, but also allows for non-trivial selection and associated with the environment. So it's a way to both get an answer of 0 when it's 0, but not force things to be 0. We can then have some estimates of effective population size, maybe coming from the same genetic data, and then you have some estimates of trait genetic architecture. These can be known and fixed, or they can be, the uncertainty of those can be incorporated into the model, into the analysis. And sample from all this, you get your selection differential. From the math above, you get the selection of individual loci. You can simulate evolution across time and space. You get summary statistics and derived parameters I'll talk about in a second. And then use whatever your favorite ABC summary is to get your posteriors. Now, the two summary statistics I focus on capture most of the variation in the model and in the most information in the data. The first one is the sum of the expected change in breeding values, or the expected polygenic scores across space and time. It tells you about the average strength of selection. The other is the overall covariance between change in the polygenic score or breeding value with the environment. Those are our two summary statistics. We can also get derived parameters that aren't sort of part of the inference of the model, but things we can estimate too, such as the average absolute value of selection on individual loci, average selection on loci, and the variation in those things. So here I'm going to focus on a set of core sort of conditions to start. 10 populations, 10 generations, 100 loci that affect the trait heritability of 0.3, effective population size of 500, and effect sizes drawn from a normal distribution. Here we're looking at 300 of the simulation outcomes, where we're estimating the mean selection differential at the thing I called A a second ago, and then the environmental effect might be from the linear model. The blue dots are the right answer, the black dots are the posterior point estimate, the vertical bars are the 95% credible intervals. Looking at this, it looks pretty good. The absolute errors are low, 0.0028, 0.0025, and the 95% credible intervals cover the true value about 95% of the time. That's really happy. I can show it to you like this too, where it's the estimate against the real answer. That almost looks fake. It looks really nice. I can look at it in the context of one of those derived values. This is the average absolute intensity of selection on a locus. It's pretty good too. Low error rate with 95% credible interval coverage. I can parse it by the strength of selection. So here's the mean absolute error, 95% credible interval coverage for things that are weakly selected, 0. Mildly selected, stronger. Again, the selection differential level here. Here's the average effect, the effect of the environment. Overall, it looks really good. We do particularly good when the answer is 0. We get 0. The worst is probably when you have weak but non-zero selection, because you get a bit of shrinkage back towards 0. So next, I wanted to see how to break it. I tried some different conditions to see what doesn't work. What I've been looking at so far is in the red. From that, I cut the effective population size in half. That's the blue. The green is having 1,000 loci, where we don't know for sure which ones affect things. The purple is cutting the sample size to 5 generations, 5 populations. And the orange is having that step function instead of the linear function. All those work pretty well still. Good 95% coverage, low errors. Do a little bit worse with some than others, but it's all still pretty happy. The yellow bar is the one that kind of breaks it. That's instead using individual-based simulations, assuming a Gaussian function for selection that stabilizes selection, and with the optimum of that function, or with the optimum tied to the environment. So it's really kind of the wrong model at that point. And with that wrong model, because then we do have the 95% credible coverage drop way down, and the errors go up. So far, when you have the right model, it works well. When you don't, not so well. Here's the results of that bad model. You see, you still have a good relationship overall between the estimates and the true values, but it's much weaker, and we see shrinkage of estimates back towards 0. So performance drops pretty substantially when the model's wrong. So from that, I wanted to think some about, well, okay, how do we know when the model's wrong? How do we know when it's wrong enough to really care anyway? So just as an example, thinking about this, here's results from a single analysis where the data were simulated assuming directional selection, assuming a linear function for selection as a function of the environment. The true answer is this black line here. I fit the model with the linear function that in our model, and I get the blue line here is the best estimate, 95% credible intervals. The pink or red is the same thing fit with the step function. Well, so here blue's better, right? But you really don't know what the right answer is. So how do we want to think about whether the model's out of garbage or not? We can use a posterior predictive check for that, where we simulate some other aspect of the data and ask whether these different models do a better job of fitting it. So remember the two sub-statistics I had before were the total change in the polygenic score, or the expected breeding value, and the extent to which it covariated from the environment. So I don't want to use those, in part because they don't tell me very much about these alternative models. They're great for fitting the models, but not for comparing them. I want to use something else. So I'm going to use a different summary statistic that I didn't use to fit the model. Here I'm going to use the percentiles, 10th, 20th, 30th, up to 90th percentile of the change in the expected breeding value or change in the polygenic score, and ask whether one of the models does a much better job of matching those than the other model. The answer is they do. So the black line is the true answer. Different quantiles of change in the polygenic score. The blue distribution is what you generate over the posterior for our model fit with the linear model. The red is when you generate over the posterior for the model fit with the wrong model, with the step function model. And the step function model doesn't line up very well with the right answer. The blue does. So we can use the posterior predictive check, which uses mostly independent information, as a way to ask whether this model is worth the crap or not, or whether it's not a good fit for the current data set. So with that, I want to conclude. So I think the model I have here can generate accurate, precise estimates of selection on a polygenic trait when it's fluctuating selection, which is pretty cool. And I think this way it's set up is nice as it connects from thinking about traits to the environment to selection to evolutionary change, sort of puts it all together. I think there's rich information there. The flip side of that is that it works well when the model's right, not so well when the model's wrong. So you don't have an understanding of the environmental context of what you're driving selection, you don't have the right traits, have poor mapping of the genetic structure. All those things can start to break it. So you have knowledge of the system, you can do a lot with it, you can list otherwise. Currently I'm working on extending this to quadratic selection, thinking about multiple environmental covariates, multiple traits, and G/E for the effects of traits on, for the effects of the genotypes on the traits, so that you can not only have selection vary with the environment, but the genetic basis of the trait vary with the environment. I'm putting together data to use in cases like this, but I'm looking for more data for this, where you have that time series information to try it out. With that, I want to say thanks for listening. And anyone who's interested in thinking more about fluctuating selection methods and empirical, I'm looking for a postdoc and a PhD student in a year to start working on this mark. Thank you. Questions?